The stationary balloon is a project that will make us get the height from the bottom of the balloon to the part of the rope that touches the floor only by using densities and the volume. As we just said, our objective is to determine experimentally and numerically the length of the segment of the string such as the helium-filled balloon remains stationary. To get this project done, we only need a few things: a rope heavy enough to keep a balloon stationary and preventing it to go away, a spherical balloon. The shape is asked to be spherical so we can get the volume easily. Then we wait for it to be totally stationary and then we measure the height of the balloon. We can now proceed to analyze the problem with the theory and the data we know. First of all, we have to analyze all the forces acting over the balloon, the one going up and the one going down. The one going up will be defined as the force of the balloon. The one going down will be the total weight of all the system we just built. These forces will be equal to each other. Now we can break down the total weight into three different forces. This will be the force applied by the weight of the helium, the force applied by the weight of the balloon, and the force applied by the weight of the string. A force is equal to mass times the acceleration, or in this case, the gravity. So we can say each one of the forces can be expressed as mass of the helium times gravity, mass of the balloon times gravity, and finally, mass of the string times gravity. Now let's analyze the other part of the equation. We can break down the force B into the density of the air times gravity times the total volume of the balloon. Applying all the changes, this is the formula we get. We can see that the gravity is present in both parts of the equation, so we can get rid of it, obtaining the following formula. Now let's work with the mass of helium factor. By analyzing the equation of the density, we can say it is equal to mass over the volume. But here we are missing the mass. By clearing out the equation, we obtain this new formula that we can use in our first equation. This equation seems just right, but we are forgetting something: to analyze the rope. If we see carefully, we realize that we are not using the total length of the rope, but the part of the rope that hangs until it touches the floor. In our equation, we know each one of the factors but one, and it is the mass of the hanging string. So we clear out the equation to get that because it is very important part to get the height. To get the volume, we just use the formula 4 pi cubic radius over 3, getting a new result. Finally, to get the height, we use the following formula. The only missing part is the density of the string, which we can get by dividing the mass of the string over the longitude of it, getting this result. We use all the data we get and substitute it in our final equation, getting this height as the result, pretty close to the one we just measured. Here are our results.